Lesson 1.2 is on theoretical probability and odds. Today's goal is to understand the components of theoretical probability calculations and how to apply them.
Theoretical probability of a particular event A is deduced from analysis of the possible outcomes, assuming that all outcomes are equally likely to occur. It is calculated by dividing the number of desirable outcomes for event A, n of A, by the total number of possible outcomes in the sample space, n of S. So, the probability of an event A is equal to the probability, the total possible outcomes of event A, so that's n of A, over the total possible outcomes of all things that could possibly happen, so n of S. As I said, the sample space. Let's start with an example. Example 1. Calculate the theoretical probability of rolling a 1 on a 6-sided die.
Well, Miss Penna, if there's 6 sides on the die and they're all different, then the number of possible outcomes, ns, must be equal to 6.
So, Mr. Langford, since there's only one 1 on a 6-sided die and the desirable outcome or the event is a 1, then n of A should be 1, right?
That's right, Miss Penna. So, the probability of rolling a 1 must be NA over NS, which in this case is 1 over 6.
Now let's consider the sum of the probabilities of all the possible events. So, since there are 6 sides on a die with numbers 1 through 6 on each side will have a probability of 1 over 6, just like the 1. And there's 6 sides, so we'll sum all 6. One over 6, which of course is equal to 6 times 1 over 6, which is equal to 6 over 6, which of course is equal to 1. And that should make a lot of sense because when we roll a dice, we have a 100% chance of getting something. The die will always land on a number.
So then I'll say... So, Miss Penna, does that mean that if I sum the probabilities of all the possible events in any experiment with theoretical probabilities, that they would add up to 1?
Exactly, Mr. Langford.
Cool.
But wait, Mr. Langford, how do you calculate the theoretical probability of the likelihood that my mom's going to like the dress I just bought her?
Well, Miss Penna, the problem with that is there's no way to collect data doing trials to get some sort of calculation for an experimental probability, and we can't really figure out what the sample space is for the possible outcomes of how much your mom likes the dress. So this falls into the category of a subjective probability, which is like a guess from experience of what you think the probability will be.
Oh, so, I mean, in the past, my mom generally likes the dresses that I buy her, so I'm just going to say 80%.
Fair enough. Number 2.
Now it's your turn. Try to estimate the probability that you will ace your first data test that you write.
Okay, so let's try example 3 now. We're going to determine the theoretical probability of rolling a sum of 7 with a pair of dice. Just as a little hint, this requires us to find NS, the sample space, which is all the possible sums of a pair of dice. For instance, if I roll a 1 and a 6, that's a sum of 7, and that could happen 2 ways. You have to find all the 7s and all the other possible sums as well.
Now we're going to move on to the complement of an event. In probability, the complement of an event A is written as A apostrophe. And we say this or pronounce it as A prime or not A. Not A is the event where the event A does not occur. Thus, whichever outcomes make up event A, all the other outcomes make up not A. Because A and not A together make up all the possible outcomes, the probability of the event A plus the probability of not A is equal to 1.
I think I get it, Miss Bennett. That's sort of like saying the probability of the Blue Jays winning tomorrow added to the probability of the Blue Jays losing has to equal 1.
Exactly.
Cool. So the picture below of the rectangle represents the total outcomes of an experiment inside the big rectangle, with event A in a circle and all the events that are not A outside the circle. Cool.
So, Mr. Langford, does that mean that the probability of the event not A is equal to 1 minus the probability of event A?
That's correct, and this is a very important rule in probability calculations, and we should remember this when we do problems later on.
Now let's look at example 4. What is the probability that a randomly drawn integer between 1 and 40 is not a perfect square? So, take a moment, pause the video, and think of the subjective probability.
Does that mean we should take a guess?
Exactly. Okay, but what about the theoretical probability?
Well, Miss Penna, I think to do that, we need to figure out actually which numbers from 1 to 40 are perfect squares and subtract.
Okay, Mr. Langford, I've written down all the possibilities between 1 and 6 that have perfect squares between 1 and 40. So, since there are 6 perfect squares between 1 and 40, the probability of event A, where event A is equal to drawing a perfect square between 1 and 40, is equal to 6 over 40.
But Miss Penna, I thought we were trying to find the probability that it was not a perfect square.
Well, exactly, and that's where we can use the formula we just learned. Since the probability of not A is equal to 1 minus the probability of A, which is equal to 1 minus 6 over 40, which is, of course, equal to 34 over 40.
So we could also write this fraction as 17 over 20, or 0.85, or say that there's 85% probability that it's not square. Okay, so now you can try using your TI calculator to generate some random integers between 1 and 40 in an effort to find the experimental probability of drawing a number that is not a perfect square. Remember to predetermine a number of trials that you're going to do before you conduct the experiment. Then you can compare your experimental probability result to the theoretical calculation that we made a few moments ago.
And try to complete the following sentence. Experimental probability approaches theoretical probability as the number of trials approaches blank.
Okay, Miss Penna, how come I'm always hearing people say things like, what are the odds of that happening?
Well, Mr. Langford, odds are actually very important in probability. Odds are used to compare the probability of an event occurring versus its complement. This is referred to as the odds in favor and the odds against an event occurring.
Oh, I get it. Like we use them in sports. For example, the Bear Fair football game on September 20th will have St. Mike's visiting TCS, where the odds in favor of TCS winning are reported as 3-2.
Exactly. Now, you may have just noticed that the notation we use for odds is a little different. We use a colon. So the odds in favor of event A is equal to the probability of event A occurring, colon, the probability of not A. And then, of course, the odds against event A would be written as the probability of not A first, then colon, then the probability of event A. Okay, let's try another example. Example 5. In a deck of tarot cards, there are 10 character cards, 3 of which means bad times ahead, 7 action cards, 3 of which means bad times ahead, 6 object cards, 3 of which means bad times ahead, 14 wands, 14 cups, 14 swords, and 14 coins. When randomly choosing one card and assuming that you believe in luck more than you believe in fortune telling, 1. What are the odds that you are doomed?
Well, Miss Penna, that's a lot of cards, but if I add correctly, it looks like there's 79 cards in the deck. By my count, I think there's 9 cards, which mean bad times ahead. That leaves 70 cards that seem okay. If I compare the bad times ahead to the stuff that's okay, I'll get the odds that I'm doomed. So it looks like for the odds that we are doomed, it should be 9 to 70.
But wait, Mr. Langford, how is that any different than the probability that you're doomed?
Well, probability is different because probability compares the number of cards that say I'm doomed to the number of cards in the entire deck. So here the probability of being doomed would be 9 over 79.
Oh, okay, I get it. Now on your own, try example 6, the roulette table. Given a standard casino roulette table, which is shown to your left here, calculate the odds of winning on a red bet. And how has this casino used psychology to their advantage?
So if I found in example 6 that the odds of winning on a red bet are 18 to 20, then how do I change those odds into a probability of winning on a red bet?
Well, since we know that odds are written by comparing the probability of an event A to the probability of the event not A, and in this case, that's the probability of winning on a red bet compared to the probability of not winning on a red bet, so 18 compared to 20, we know that n of red is equal to 18, and n of not red is equal to 20. And furthermore, the entire sample space is equal to 38. And since we know that probability is equal to n of red over n of the sample space, we know that the probability of winning on a red bet is equal to 18 over 38. For homework, try examples 8 and 9 and bring your answers to class.
Be sure to bring your textbook to your class the next time you come so we can work on the problems on pages 24 and 25 together.